confusions will be removed, I really want that. I want this. Yes, please go ahead.
About the participants online. They are also our teacher. If you check, there are some of them. They are professors also. They are doctors. My Egypt said when he come to tell on the stage, he said my teacher. He saw us. He was up to him. I saw you. That means, mashallah, your class is very important, not for us, for the participants that they are online. I know that some of them they are also teachers in the universities.
Yeah, and Sami sent me this letter also in which you were all acting like protons of ethanol. Okay. And you were on the transverse plane moving to record FID. And one of you was slowest, the other was the fastest. Anyway, I think NMR, I believe NMR can be taught uh, in person, to be honest, because uh, when you are present there with the movement of hand or something like this, you can explain many things much effectively than online. So inshallah, next week we will have class on 26, 27, 28, and 29th. Okay, inshallah. And we will try to have all everything confusing to be clarified, because I think the best way of learning is to ask questions. And maybe if we first lecture, we will just have questions and answers, nothing else but questions and answers. Uh, I know there are a lot of interest in NMR, and as I mentioned that except proton NMR, which can be explained, or C13 broadband NMR, which you can explain by absorption theory, or the old conventional continuous wave theory, all other NMR experiments can only be explained through this new theory, which is called pulse Fourier transformation. Good. I give the example broadband decoupled, in C13, in which you see one signal for each carbon, cannot be explained by absorption. How would you remove proton signals? Coupling, how would you remove proton coupling with C13? So that you can only explain by pulse. You can only explain that you have to remove hydrogen from this coupling dimension and that you need to take it. So from that very simple experiment of decoupling all the way to three-dimensional NMR or multi-dimensional NMR, which Dr. Atia is an expert, can only be explained by pulse Fourier transformation, by vector diagram, by FIDs, by understanding the uh, the rotating frame of reference. What is happening? All the entire stage of NMR is on XY plane. Entire stage of NMR is on XY plane. Everything happening on XY plane. The game is going on in XY plane. The football is going on in XY plane, because your detector is there. You're recording FID. You have all your all your vectors, magnetic vectors, your elements, NMR active elements on XY plane. So what is going on XY plane can only be explained by vectors and can only be explained by rotating frame of reference. I told you that these vectors are moving with their Larmor frequency. Larmor frequency is equivalent to radio frequency. Radio frequency is the speed of light. And imagine that on XY plane, if everything is moving with the speed of light, can you ever understand which vector is positioned at what? They are just so fast that you cannot imagine. But if you are on one of the needles, on one of the vectors, then you will see only the difference in velocity, right? And then you would know exactly where are the other vectors. And when you know that, for instance, if you have five vectors, five different types of protons, then you know which one is moving faster, which one is moving slower, because you are part of the system. If you're outside, they all are moving at the speed of light, with a little difference which is negligible. So these can only be explained through these concepts. Number one, vector, Boltzmann distribution axis, vector. Number two, pulses. Number three, rotating frame of reference. And number four, FID. Number one, Boltzmann distribution axis, this net magnetization difference, which is comprised of all net magnetization, which is excess in low energy state, M naught, which is comprised of many. And then pulses. You give a 90 pulse, where they will come. If you give 90 pulse from one side, it will come on the other side, So this pulses, the direction of pulses and power of pulses. What happened in XY plane can only be explained through rotating frame of reference. Can only be explained. Because, next step, when you play with the second pulse, it can only be explained when you know where the vector is, right? And then you record FID, and FID is then converted into Fourier transformation. So today is largely a practical session, and my colleagues will try to link this theory with experiments. Okay, all this theory is not theory. Everything is implemented. Everything is performed in experiment. So, for instance, today they will tell you how to prepare sample. Okay, liquid sample. Why it is important to use deuterated solvent. Why not you use protonated common solvents? Why you need to have deuterated solvent, which are so expensive? Why it is important to have complete solution? The dissolution and solubility has to be close to 100%. You cannot afford to have solid particle in your sample, because they will tell you that there are problems like T1. Relaxation would be very fast because it will find some ways of transferring the energy, and you don't see any signal because all the energy will gone, so your FID will not be like this. Your FID will be like this, quick. So no solid particles. It has to be dissolved particularly. And then they will tell you why it is important to rotate your sample on the airbed, because they'll tell you that when you rotate your sample, you ensure that every region of the sample, to some extent, is receiving the same magnetic field. Remember that magnetic fields are absolutely wonderful. They are very, very stable and homogeneous, but they're not 100% perfect. They still have differences in the region, They still have a few minor differences, which is called magnetic inhomogeneity. And when you rotate the sample, for instance, if I have this, slightly more magnetic field this side, right? So if I rotate it, then all part of the sample will have essentially the same magnetic field. So they'll tell you why it is important. And the most important part is, as I said, that rotating samples through air current, is because that you want to make sure the effect of magnetic imperfection or inhomogeneity is reduced. They will also tell you that how many pulses you need for a common proton NMR, and if you're recording a C13, why you need to have more pulses, more skeins, because C13 is only 1.1% naturally abundant. It has a four times less gyromagnetic ratio. It is a poor magnet, and therefore you need to have more skein, more pulses, in order to improve signal to noise ratio. So many practical things will be shown today, and to try to link the theory with the practical. And from 26, 27, 28, and 29, 4 days. 26, we will have only question and answer session, and everybody, no matter how simple, trivial, any question, I would like the first day on 25th only question and answer, Q&A. And I would be really sad if you don't ask question. Any question which you feel you don't, it doesn't clarify. Because there is a very famous Chinese proverb that if you ask a question, you may look stupid today, but if you don't ask a question, you remain stupid for rest of your life. Okay? So ask question today, and you should not ashamed of asking question, because questions are asked by people who are curious, who wants to know. And this is the first and most important attribute of an alim. Alim, scholar. So it is the most important thing. Alims are the one who ask questions. They start from a question and they end with the question. Every question give you an answer, and every answer again give you a question. This is the reason why it's called research. Remember, it's not search, it's research. So this is the first day we will have question and answer, very very simple. Then on 27th we will start again, and by 29th we'll try to go to two-dimensional NMR. And then there will be another practical session in which they will show you how two-dimensional NMR spectrums are recorded. The procedure of sample preparation is same, just the pulse sequence is different. Because in two-dimensional NMR spectrum, you just add one thing, and that is time delay. When there is a time delay before you turn on the detector, the vectors are gone somewhere else. It's like you are watching a football match, and if you just for a minute close your eyes, delay, and you open it, the player has gone somewhere else, right? He has a ball, he has given to somebody else. So you then know that with the dimension of time, what changes you expect in your NMR spectrum, and that is the second dimension. Nothing very very serious or nothing very fancy. It's just a very simple concept of watching what happened to the vectors when you turn on detector or close your or open your eyes after some time. After 1 second, Messi is there. After 2 seconds, Ronaldo has taken the ball and gone to their side. Or that very famous Moroccan player, what is his name? Uh, yes. Okay. He has taken out that. And now Saudis have hired everyone. So Saudi will hopefully will win World Cup. So it's just understanding that with time, when you open the detector, where the vectors are. So I know that there are so many questions, but then, eventually we will try to answer them and to have a more detailed discussions. Okay. So, Professor Attia, you like to show us some practical videos?
Yes, sir.
Okay. Until she shows you practical session, I'll show you some of that.
Okay, sorry.
So you see Prime Minister Secretariat.
सर सर दोबारा दिखा दें, वो मैंने विंडोज डाउन कर दी.
Okay. Our Prime Minister is sitting there. Our Supreme Court judge is sitting there. And beautiful mountains.
Sir,
And
you have a very auspicious, amazingly beautiful, fascinating office. MashaAllah.
This is the best office in Islamabad. With the
That's true.
most wonderful view of Margala. Yes. And inshallah, we'll invite all of you to Islamabad, inshallah. Okay, you can start now.
Inshallah. Sir, they are clapping and saying thanks.
Thank you very much. Thank you.
See like option complete successfully. Also, you can
Nuclear magnetic resonance, NMR, is probably the most important technique for finding the structures of organic compounds. So much so that there is a saying, when the NMR goes down, the organic chemists go home. The principle of NMR is based on the fact that certain nuclei with odd atomic mass or atomic number, such as hydrogen 1, carbon 13, fluorine 19, and phosphorus 31, have a property called spin.
Okay, I would like to ask you that in the video that they are showing that these are the nuclei that can be observed in NMR. Why? Huh? Why you can observe these? NMR active nuclei. Odd number of?
मैम वीडियो ऑनलाइन शो नहीं हो रही है.
यदि स्टॉप की है एक just a minute please. So and in chemistry mostly we are actually we used to observe proton NMR, C13 NMR, F19 NMR, and P31 NMR, right? But there's a beauty of NMR that is, I think that's the amazing thing in NMR, that you can select which nuclei you would like to see. If you like to see proton, then you can select proton. And if you like to see fluorine, then you can select fluorine. So no other spectroscopic method can have this advantage. So that is the beauty and fascinating thing in NMR.
That they have a magnetic field similar to that of a bar magnet. When placed in an external magnetic field, these nuclear magnets can line up in one of two ways.
Okay, now another question, looking at this. So the large magnetic field is your magnet, okay? Your which symbol it denotes? B naught, right? And what about the small tiny magnet? What are these? Huh? Nuclei. Why it is behaving like a tiny magnet? Hmm? Yeah, and charge, yeah. And it is spinning, right? Okay. So now you can think that tiny magnets in the magnet, all right?
With or against the applied field. These two different states have slightly different energy levels. Electromagnetic radiation, which has an energy corresponding to...
Okay, now another question from this. You know, everything you have already read, and it is discussed by Professor Iqbal. So they are saying there are energy levels. So the question is, what was the reason that NMR spectroscopy was developed at the latest? Means like the most late technique that was developed.
You
Yeah.
know,
Yeah. Yeah. So why the spin states are created? Okay, so question is, do you have, whenever you have the sample in NMR tube in your hand, do these samples have these protons or whatever nuclei, they have the energy difference?
no,
Yeah, exactly. If it is outside the magnet, then then there are no difference in energy state.
The gap between these two states can cause these nuclear magnets to flip from a low energy state to a high energy one. The size of the energy gap determines the frequency of radiation required. Each element has its...
Okay, now another question. So when you have like 300 megahertz NMR and you have 800 megahertz NMR, so why the sample which is recorded in 800 is or 800 megahertz is more sensitive as compared to 300 megahertz?
low energy station, high energy station, become bigger because we typically more can be absorbed. We make this gap is bigger radio frequency, which can be absorbed.
Yeah, good. So when you have greater the strength of the magnet, then you have bigger and bigger energy difference between the alpha and beta state.
its own particular frequency, but they all lie within the radio part of the spectrum. We will concentrate on hydrogen 1 NMR. This is often called proton NMR because the hydrogen nucleus is just a single proton. As they drop back from higher to lower energy states, the nuclei of hydrogen atoms in different positions in the molecule give out energy at slightly different frequencies, and this can tell us a lot about the structure of the molecule. For example, in ethanol, CH3CH2OH, the 3 CH3 hydrogens will give a slightly different frequency than the 2 CH2 hydrogens, which will be different again from that of the single OH hydrogen. This energy is picked up by a receiver in the instrument.
Okay, so the question is, there are 3 different types of protons. So how many signals do you expect? How many type of the signals? Or if there is a chiral center there, then how many signals would you expect? If there is a chiral atom, a chiral center. For each proton, whenever there is a chiral center in the molecule, so that has a very strong impact. So each proton appears as a different chemical shift, right? So the chiral center has a very strong impact in any molecule.
And looks like this. A strong signal gradually dying away. This is the total signal from all of the hydrogen nuclei in the...
What's the name of this spectrum?
Decay.
Hmm?
Decay
FID, free induction decay.
Sample and is very difficult to interpret. However, a mathematical technique called a Fourier transformation can be used to separate out the signals from hydrogen atoms that are in different molecular environments and present them as a spectrum that can be interpreted by chemists. This is a typical NMR instrument. The magnet is a superconducting one and is housed inside the cylindrical metal casing. It is cooled to 4 Kelvin in a jacket of liquid helium, which in turn sits in a jacket of liquid nitrogen at 77 Kelvin.
What is the function of liquid nitrogen here?
Actually,
Hmm? Yeah, actually, helium magnet is immersed in the liquid helium, right? And but liquid helium is expensive, very expensive. So if in this diver, it's a diver, you know, magnet, wherever your magnet is actually a diver. So in the diver, if helium has outside a vacuum and then the regular atmosphere, then the evaporation rate of the helium is very high. So the purpose of jacket of liquid nitrogen around the liquid helium is to slow down the evaporation rate of liquid helium. So liquid helium is always evaporating slowly and gradually. Yeah, but the liquid nitrogen is actually the only reason that liquid nitrogen jacket is around is to slow down the evaporation of liquid helium.
what's the function of helium?
Liquid, your magnet is immersed in the liquid helium. So why? Okay, so what is the temperature of liquid helium? No, what is the temperature? I'm asking you.
No.
Why you don't know after so many class?
Tension in the slides.
Dr. Iqbal told you several times. What is?
In the minus.
What is minus? Minus what? Minus 0, minus 1, minus 2, what? Huh?
Minus 200.
Minus 273?
It's nice.
Huh?
But the helium. Helium
Yeah.
at 3 degree Kelvin. It's minus 420 or minus. But nitrogen, it's ask everyone here.
No, you ask the question. So you should answer first.
That's it. I mean, my situation is the same. Like,
Yeah, I want to know. First, you answer. What is the temperature of liquid helium?
I know. Remember the number.
You should know.
The minus.
What is minus? You know, minus 1, minus 10, or degree centigrade, or degree Fahrenheit, or Kelvin, what?
What's my question? If you focus
First, you answer. You need to answer. I want to answer your question, but it actually depends on your answer first.
269.
What? 269 what? 269 Celsius. Huh? Okay, so now I will answer your question, but you have to tell me. Now you will study this and tell me. You can. No, you have to know about, you know, this is what we are learning. You know, Dr. Iqbal is teaching like 10 classes. And even you don't remember the temperature of liquid helium. So how would you understand the function of liquid helium?
I have practical about this, and I see helium.
You can never have the practical for this.
Fully, but as all of
Do you, okay, just think about, liquid nitrogen is commonly available in the labs and everything, right? And can you have the practical of touching liquid nitrogen? What about, huh? Can you? Huh? Then,
and boron.
yeah. So how would you have the practical of liquid helium?
The helium lower than the helium.
That's, you should know now, okay? In the next class, or maybe tomorrow or day after tomorrow, I mean, like Monday, you can come to me in my lab, but you have to tell me what is the temperature, and then I will explain you what is the function of liquid helium in NMR spectrometer. Okay?
With the answer now.
Huh?
The answer is answer my question. What's the function of helium?
First, you need to tell me the temperature.
Or isolated the noise from outside.
Why we just need the vacuum to isolate the noise and everything. Why we need liquid helium.
Okay. If the helium is the low temperature.
Okay,
my
for you, I would like, first, I understand your question, I understand your curiosity, but I think it would be better that we have to have like one-to-one meeting in my lab, specifically for you.
The second question.
You can keep your question till that time. Okay, we can just proceed for the class because we have to go to the visit as well. And on Monday, I will be waiting for you in my lab, but with all these knowledge in your mind. Okay.
Now you will come to me.
The
Huh?
magnet uses a current of 50 amperes, which,
you.
once started, flows continuously as the coils have zero resistance at 4 Kelvin. The sample sits in the center of the cylinder inside this probe, which contains the coils that send and receive the radio frequency signals. The electronics which generate and interpret the radio signals are housed in the boxes to the left. Samples are placed in the machine and removed from it by the auto changer, which takes the samples in turn from the carousel. The instrument is controlled from this workstation. This bare probe shows the radio coils and where the sample sits.
You have seen this probe last time, right?
Here we will run the proton spectrum of ethanol. A small amount is taken and dissolved in deuterated trichloromethane. This solvent is trichloromethane, in which all the hydrogen atoms have been replaced by deuterium. This is so that the signals from hydrogen atoms in the solvent will not be mixed up with those in the sample. A little tetramethylsilane, TMS, is often added as a reference. Each molecule of this has 12 hydrogen atoms, all in exactly the same environment. The signal from these is taken to be the zero of the spectrum and has the value of 0 parts per million. Inside the instrument, the sample sits on a cushion of gaseous nitrogen. This plastic spinner has vanes that turn in the flow of nitrogen and spin the sample. The spinner is placed on the tube in such a position that the sample tube will be in the center of the magnetic field when it is in the instrument. Together, these ensure that the sample experiences a uniform magnetic field. The operator places the sample in the auto changer and tells the computer the identity of the sample and which position in the carousel it is in. The auto changer selects the correct sample and places it in the instrument. The sample is lowered gently into the probe on a cushion of nitrogen so that it sits in the center of the magnetic field and the radio coils.
We have only one auto sampler in our institute. attached with the 600 megahertz.
Under the control of the computer, the instrument applies several, typically 16, pulses of radio waves to the sample and collects the responses, called resonances. These resonances are summed up by the computer and processed to give a spectrum. This takes about 5 to 10 minutes. Here is the spectrum of ethanol. The peak to the far right is that from the TMS reference. By definition, this is at 0 parts per million, ppm. The distance leftwards along the horizontal axis is called the chemical shift, and it is measured relative to the peak that is obtained from the hydrogen atoms in TMS. The chemical shift of a peak gives information about the molecular environment of the hydrogen atoms that it represents. The peak at around 1 ppm is caused by the CH3 protons. That at approximately 1.6 is the OH proton, and that at approximately 3.5 ppm is from the CH2 protons. The area under each peak is proportional to the number of each type of proton. This is calculated by the computer and represented by the step height of this integration trace. A closer look at the spectrum shows that the peaks are in fact split into groups of peaks called multiplets with particular patterns. This is called spin-spin splitting. It is due to the influence of the magnetic field of adjacent protons. Two adjacent protons split a peak into 3 with heights in the ratio 1 to 2 to 1. And 3 adjacent protons produce 4 peaks with height ratios 1 to 3 to 3 to 1. This is sometimes called the n+1 rule. Interpreting proton NMR spectra can thus provide a great deal of information about molecular structures. The same instrument can be used for NMR of other magnetic nuclei. A useful one for organic chemists is carbon-13 NMR. All that has to be changed is the frequency of the radio signals.
Hello everyone. On today's video, I'm gonna
Okay, meanwhile, when he's sharing the video, I would like to answer your question, but you should know what is the temperature of liquid helium and liquid nitrogen. Now we are having superconducting magnets, right? The electronics are different. Before superconducting, we had electromagnet. And before that, we have solid magnets like the one that we are, children are playing. So superconducting magnet, as the name shows, it is fully magnet. It is once charged. It is charged when the NMR is installed. So once it is charged and it remain magnet till it immersed in liquid helium, because at that temperature, the resistance is ideally zero. And when the resistance is zero, the magnetism remain constant. But as soon as liquid helium evaporate, finished, and from the magnet, then the magnet quench. Okay, and then it require uh, maybe $0.5 million or $0.3 million to reinstall, because the magnet need to be charged again. And while charging, I would share my observation when we were the only magnet when it was in 2016 to 800 megahertz NMR, when it was installed, that I have seen myself, that the Bruker engineer, when he was charging, while charging, is just quenched. Huh? Charging the magnet. Installation. Right now, installation, there is no sample. Yeah. B not. No, it's not a permanent magnet. Permanent magnet was actually at that time when the NMR was invented as a spectroscopic technique. Then at that time, there was a permanent magnet. And then there was an era in which NMR has electromagnet. Now we do not have either of these. We have superconducting magnet. That means the magnetism of the magnet will remain until it is immersed in liquid helium at that temperature. Okay. Well, helium is not doing anything. Helium is not doing, because at that temperature, and that temperature you should know. Okay, at that temperature of liquid helium, resistance is ideally zero. When the resistance is zero, then the conductance is maximum. So once it is charged, it is not charging all the time. The magnet is not charging. It is only charged when the magnet is installed. Okay, and it will remain magnet till it is immersed in that temperature. And that temperature can be if you can bring that temperature by something else, then it's fine too. All right.
Very low. Cannot affect the survey to make it.
Yeah, very good question. I enjoyed this. That is the technology. A few that Dr. Iqbal also mentioned in his lecture, that a few millimeter away, you can not only have the room temperature, you can increase the temperature and you can decrease the temperature. Just few millimeter away of the coldest thing in the world, you can have that much control. And even he said in one of his lecture, even you build this magnet with the gold, then it's cheaper than what we actually purchased. The 800 megahertz that we purchased is $2 million. And that was in 2016. Right now, it is $3.4 million. So it's very expensive technology. It's the cost of technology that we pay. Okay. So these equipments are very sophisticated, very advanced, state of the art, but it's the cost of technology. And you can think about it, that few millimeter away from the coldest thing in the world, you have that much control that you can do whatever. You can select whichever nuclei, you can increase temperature, you can decrease temperature, you can increase temperature up to the boiling point of solvent. You cannot go to the boiling point because solvent will be evaporated and it's a liquid NMR that we are discussing. all right? But you can decrease the temperature before the freezing point of the solvent. So you have that much control. And is the cost that we are paying is the technology cost. Okay, that's Dr. Iqbal also mentioned in, I think, first or second of his lecture. All right, so we have another video to play.
Nuclear magnetic resonance is a technique that uses magnetic fields and electromagnetic frequencies to study molecular structures. For high magnetic fields, superconducting magnets are used. Lower fields can be generated by permanent or electromagnets. Samples are inserted in the center of the magnet and are positioned in the NMR probe. So the sample is located at the position of the strongest field and highest homogeneity of the magnet.
So here you could see that the NMR tube, it is placed on the probe, right? And the magnet is around this. And this magnet need to be immersed. It will remain only magnet till it is immersed in the liquid helium. And that is why helium we have to refill in our magnets every 3 months or so. But it's not like refilling is we have a point. For example, when we fill it, so it may be up to this point, then it must to this is the lowest point that the helium need to be refilled. And the liquid nitrogen, it is very close to the atmosphere, and that we need to fill every week. So we cannot refill liquid helium every week, it's very expensive. But liquid nitrogen, we have our own plant of liquid nitrogen. We are preparing liquid nitrogen in our institute. And we also have a plant of liquid helium in which all these helium which is evaporating, it is collected in a big balloon and it can re-liquefy. But we use it whenever it is very much needed or there is a shortage of liquid helium. Because without liquid helium, all magnet will quench.
Of the magnet. The NMR probe consists of coils that are used to excite the sample and record signal responses at radio frequency. The basis of NMR is that nuclei behave like microscopic magnets in a magnetic field. They spin around the main magnetic field just like a spinning top. This motion is called precession. The frequency of the precession is proportional to magnetic field strength. Additional local field differences are introduced by changing electron densities in a molecule. A higher electron density results in more shielding and thus a lower local field and lower spinning frequency. In NMR, the frequency of the excited nuclear spins can be measured from the electric current they induce in the coil. Fourier transformation of the time domain signals results in the frequency spectrum, with a signal for each different nucleus. The different frequencies we call chemical shifts, as they depend on the chemical structure of the nuclei. In practice, spectra are measured for all hydrogen nuclei at once, which results in the ethanol spectrum with 3 different peaks at different chemical shifts. Since nuclear spins behave like magnets, they also influence their neighbors. One way this happens is through shared electrons in the chemical bonds in the molecule. We call this J-coupling. Each spin can have 2 states, along the magnetic field or against the magnetic field. As an example, we look at the 2 methylene hydrogen spins, which are chemically identical. They can have 4 combinations: 1 spin down, 1 up, both spins down, 1 up, 1 down, 2 spins up. Each combination has a different energy level and influence on the neighboring spins, except that up-down and down-up combinations have the same energy level and influence. The influence is visible as a splitting of the signal of the methyl group into 3. This is called a multiplet. Likewise, the 3 methyl hydrogen spins split the methylene response into 4 signals. In conclusion, NMR can identify molecular structures from chemical shifts and multiplets.
Do you understand this splitting pattern?
Like it. I understand it because it is the component.
Okay, so if everyone understand, then we'll stop here.
Can you
Now.
explain it?
What?
In this video,
Yeah.
hydroxyl group appeared after CH3 and CH2, and the previous video appeared after interaction between CH3 and CH2.
Hydroxyl actually is an exchangeable proton. So you only observe when you have recorded spectrum in BMSO or some kind of solvent where you can see the hydroxyl group. Otherwise, if you record your spectrum in methanol, so it's always exchanged. And their chemical shift also very depends on the hydrogen bond. So if it had it depends on the hydrogen bonding where it should appear. So you cannot sometimes predict the value where it should the chemical shift of the hydroxyl group. It depends on the intra and intermolecular hydrogen bonding. Or this is a small molecule, so there must be intermolecular, but when there are several hydroxyl groups or any other like carbonyl group or something there where it can form the hydrogen bonding. So there might be intermolecular or intramolecular interactions that actually change the chemical shift of hydroxyl group. So most often when we are elucidating the structure of any molecule, we do not pay that much attention of the chemical shift of hydroxyl group. And sometimes we, if we want to observe because of just a prediction or something, then we have to use a solvent like BMSO, in which we could see hydroxyl group chemically. Exactly. Otherwise, sometimes it just doesn't appear as well. Yeah. Yes.
Is it applicable on the protons like also for SH?
Yeah. Yeah. Exactly the same. Yeah. If you have hydroxyl group or SH, it behaves exactly the same. And that's what chemistry is. You know, all the group in the periodic table, the atoms in the group, usually have the same chemical properties, or the reaction mechanism would be the same, right? But they're definitely the electronegativity is different or is getting lower when you go down the group of the periodic table. But the reaction, the pattern of the reaction or the reaction mechanism is almost the similar, but slightly different, but you can always predict and understand based on the atoms present in the group of the periodic. Right. Okay, so we will now move to NMR lab, yes?
And these
Yeah. Okay, so they are not charged because because of the hydrogen bond. Yeah, if you really want to observe, so you can have a range of proton NMR recorded at different temperatures. You know, from lower temperature to higher temperature, then there will be sometimes, you know, at some certain temperature, the peak will be sharper and then it gets broader. So it depends on the temperature. So if you really interested in the behavior of the hydroxyl group, how it is behaving, or what could be its hydrogen bonding, so you can predict the hydrogen bonding. You can study the hydrogen bonding, but you have to have the series of proton NMR spectrum Exactly everything needs to be the same, only the temperature. The rest of anything, if you whenever you are recording any experiment, that is actually you are focusing to study something, you have to keep everything constant. And but you can definitely you have to change everything constant, but the only thing you can observe, for example, the temperature, you can change the temperature, but rest of the thing need to be constant. Otherwise, you will see the effect of other changes. Then you will not be able to understand, and you might be thinking that is the effect of the temperature, but it's not the case. Okay, so everything else, we will go and discuss the parameters of NMR that you can see. And whenever you get here in our NMR lab, you get the soft copy spectrum, and there are many in the processing parameters. There are many things that you can change and manipulate and observe. That is how you learn, right? So you change the parameters from like processing parameters, like um, from sine to cosine, different type of processing parameters you can choose, and then you can see how it is actually affect on the shape of each peak in the spectrum. So that's how you learn, and you can manipulate and window functions, all these kind of things. But you have to play around the software, and that's how you learn the software. Okay, but you can definitely do it in processing whenever you get the soft spectrum. Okay. Any other question? All right. So now for online participants, you can we are actually going to our NMR lab, and probably in next time, or we will think about the time and discuss with you, and we set up for the NMR how to process and show you our NMR lab. Not this time, but we will next week. Probably we will be able to arrange everything video conferencing in one of our NMR lab and then show you. But today, for the in-person participants of this course, we are taking them to our NMR lab. But for online participants, we will communicate the time to you later in coming days, so that we can arrange all requirements that can actually show you how we process the NMR and how we run the NMR spectrometer and show you our lab. All right, thank you so much.
Dr. Atia,
Yes, sir. Yes.
I think in the
Yes.
chat box, there were comments that some of these videos were not visible to online participants.
Sir, we will share
I suggest
the
that
link.
you share links with them.
Yes, sir.
And if any one of you, I don't know whether it's possible to have online demonstration there?
Yes, sir. That's what I just explained to them, that in coming days, maybe coming week, we will set one time and then set up all the required stuff in one of our NMR lab only for the online participants. But today we are just taking the in-person participants to the lab, and coming week we will demonstrate only for online participants after setting up of the required stuff in NMR lab.
Okay, so among all of the online and in-person participant, the 10 best in terms of their assessment and interaction, and participants will be provided free ticket to Islamabad for an extensive workshop here, 1 week in Islamabad. Okay, and everything would be sponsored. We would have an extensive discussion We will take you to some NMR labs in Islamabad as well, and that include online. You know, even if someone is coming from abroad, they will be sponsored. Okay, and our students as well.
Thank you, sir. Everyone is so happy.
But participation, attendance, engagement is important. Fully sponsored ticket, stay, everything, and extensive NMR workshop, half a day, and half a day sightseeing.
Oh. Thank you, sir.
Okay.
Yeah, everyone. 10 students. 10
And if
best students.
they recommend that we can, that Dr. Atia can be invited, only on your recommendation, we can invite her also.
I hope, sir, at least some of them can recommend me.
Okay, Assalamu alaikum. Thank you.